The following API training program consists of a videotape and a student workbook. The video presentation is not a standalone training program and should not be used without the accompanying workbook. All participants should be given a copy of the workbook titled An Introduction to Fluids.
The hydrocarbon industry is one that's based on the chemistry and physics of petroleum. With these sciences come complicated equipment, essential measurements, and unique hazards. Hydrocarbons are compounds that contain hydrogen and carbon. They are, for the most part, in the fluid state. That is, they have no definite shape and they flow.
In this program, you will learn about structure, the form that fluids take, and the arrangement of molecules. Pressure, what pressure is, and its effects on fluids. Temperature and heat, we'll see how they're different. The measurement of temperature and pressure, the instruments and units that are used in our industry. Density, we'll define it, learn how to measure it, and learn of its importance in hydrocarbon products. And viscosity, what it is, how to measure it, and how it changes with temperature.
Before you study fluids, you need to know some basics about matter.
All matter is made up of atoms. Groups of atoms are called molecules. The way molecules are arranged determines the phase or form of the matter. In a solid, molecules are arranged in a rigid pattern. They're close together and have only enough energy to vibrate. A strong intermolecular attraction keeps the molecules close together. Liquids have less attraction, and as a result, the molecules can slide past each other. They have more energy than molecules in the solid phase. Liquids are fluids. Gases have the greatest speed, greatest distance between the molecules, and no rigid shape. They also are fluids.
These basics are important, and you'll be working with them directly or indirectly every day you're on the job. The fluids we use in our work are not limited to one phase. You'll encounter fluid systems or combinations of phases that have fluid properties. One example is a fluid system found in a distillation tower.
It is composed of gas bubbles percolating through a liquid. This is a two-phase fluid system.
Other kinds of fluid systems can be found at a cracking unit. In particular, the slurry at the bottom of the unit is made up of oil and a solid catalyst. This also is a two-phase fluid, made up of a liquid and a solid.
Storage tanks and supply pipes may contain fluids that are a combination of liquids. If these liquids can be mixed together easily, they're said to be miscible. The kinds of fluids that are mixed together are important in processing.
The raw materials that are processed and their products can be represented in two ways. You need to be familiar with both representations.
Structural formulas are picture representations of the compound. They will include the atoms that compose the molecule, connected by dashes. If you're given structural formulas, you have an idea of the complexity and the size of the compound. The more carbon and hydrogen atoms, the heavier the compound. Compare this compound, butane, with ethane. If you note the number of carbon and hydrogen atoms, you can see that butane is larger in size and heavier. The size, arrangement, and weight of the compound affects its physical properties. Hydrocarbons can also be represented with numbers and symbols. This is the molecular formula. This formula also indicates the weight of the compound.
At your plant, compounds like butane and ethane are processed. This will often involve heat and/or pressure. These factors can change the phase of the compound.
As the motion of molecules increases, the intermolecular distances increase. This causes expansion. All phases of matter are affected by heat in this way.
We've covered a lot about the structure of matter and its phases. Before you go to the workbook, let's review briefly.
A fluid is any material that flows. Both liquids and gases are classed as fluids. The petroleum industry deals with hydrocarbons. These are substances that contain carbon and hydrogen. Matter occurs in three phases: solid, liquid, and gas. Each has its own characteristics. Hydrocarbons can be represented with structural formulas or molecular formulas. With each, you see the number of hydrogen and carbon atoms that are present. The more atoms in a molecule, the larger its weight. The weight of the material affects its properties, as we'll see in the next period. Now, stop the tape and go to Workbook Period 1.
Well, so far in the program, you've learned about molecules, the components of hydrocarbons, and some characteristics of fluids. The next section deals with how the phases of matter can be changed by pressure and heat, and the types of fluids you'll be working with.
As you work, you use force to get the job done. Force is a push or a pull applied in a direction.
Pressure, on the other hand, is a force exerted per unit of area. It implies contact with a substance over the surface.
For example, this is a metal block that weighs 1 pound. The area at its base is 1 square inch. To describe the pressure it's exerting, we say 1 pound per square inch. The unit, pound per square inch, is abbreviated PSI.
Pressure can change matter. To determine how this happens, we need to look at molecular arrangement again.
In the first section of this program, you saw that gases have the greatest amount of intermolecular space. If pressure on a gas is increased, the molecules move closer together, decreasing the volume of the gas. If a liquid undergoes an increase in pressure, the molecules do not move significantly closer. Liquids, for the most part, have a constant volume, thus are not compressible. However, there are important similarities between liquids and gases. When they are under pressure, they transmit the force equally. That is, all surfaces that come in contact are receiving the same amount of pressure. Because of this fact, both of these fluids make ideal materials for transferring pressure.
Fluids, as well as solids, can change phase with changes in heat and pressure. The addition or removal of heat will affect the total amount of energy in the substance. This heat energy, the energy of motion, is one factor that determines phase. Another very important factor that's used to control phase in the hydrocarbon industry is pressure.
At sea level, all matter is under an atmospheric pressure of 14.7 psi. Changing this pressure will result in a change in the intermolecular space. On the job, we can do this with compressors, vacuum pumps, or instrumentation controls. Now let's look at evaporation as a process of change. Evaporation is caused when molecules overcome the intermolecular force and the atmospheric pressure that holds them in a liquid state. To do this, the molecules must move in an upward direction and have enough energy or speed to escape. If we put a top on the container of water, the same process happens, but the water vapor cannot move very far since it's confined to the area above the liquid. Periodically, the escaped molecules moving downward are recaptured by the intermolecular force of the liquid. They return to the liquid phase. This is condensation. If the system is not changed, it will reach a point known as equilibrium. This represents the point when the rate of change from liquid to gas equals the rate of change from gas to liquid. The gas molecules, or vapor above the liquid, exert their own pressure on the liquid. This is called vapor pressure.
Knowing about the effects of heat on matter, what do you think will happen to the vapor pressure as heat is added to the system?
As heat is added, the relative numbers of molecules that evaporate and condense at equilibrium are high. So, the number of molecules in the vapor phase above the liquid is greater than before. This causes a greater pressure on the liquid.
For any liquid at a given temperature, there's a corresponding vapor pressure. Another controlling factor on vapor pressure is the substance itself. Hydrocarbons vary in molecular weight. As the number of carbons and hydrogens changes, one of the physical properties that's affected is its vapor pressure. Let's examine vapor pressures for different hydrocarbons at a specific temperature.
Hexane is lighter than octane because it has fewer atoms in its molecule. If both gases are at the same temperature, the molecules of hexane move faster because they're lighter. Since this is the case, hexane needs less heat to go into the vapor state. If we could compare hexane and octane gas molecules in a closed system at 100 degrees Fahrenheit, we would find that the number of molecules is higher for hexane. This means that the vapor pressure for hexane is greater. This shows that the lighter the hydrocarbon, the greater its vapor pressure. Note also that the lighter the hydrocarbon, the lower its boiling point. Liquids with low boiling points have high vapor pressures. What happens to equilibrium if the outside pressure increases or decreases? Keeping the same models in mind, the answers are easy. Let's look at a chamber containing a liquid and its vapor. We can increase the pressure on both fluids by moving the piston down. As this happens, it's more difficult for the liquid to evaporate. More of the vapor is forced back into the liquid phase. The system is no longer in equilibrium. Conversely, if we decrease the pressure on the liquid, it's easier for the molecules to overcome the pressure, escape, and evaporate. Let's see a demonstration. A vacuum flask of water is connected to a vacuum pump. The temperature within the flask is room temperature. As the air is removed, the water begins to boil with no change in temperature. As pressure is decreased, boiling point is decreased.
By changing pressure, the petroleum industry efficiently and safely processes crude oil. Crude oil is a mixture of various fluids. In order to put them to use, these fluids must be separated. To do this, a process called fractionation is used.
The oil is heated. As each component reaches its boiling point, it vaporizes. The vapor is collected, and finally it condenses. This is also known as distillation. Because many components have extremely high boiling points, low pressure is used to drive boiling points down. Other compounds, or fractions as they are called, have very low boiling points. Most often, these are gases, and high pressure is used to condense or liquefy them. These liquefied hydrocarbons are more easily stored and transported. Another process can be used to change the hydrocarbons into useful products. This process is called cracking or reforming. It involves a chemical change of the substance. As the chemical is changed, its physical properties and uses are changed. You've covered a lot of material about pressure in this section, including how pressure affects phase, how vapor pressure varies with temperature, weight, and boiling point. Equilibrium is a balance between evaporation and condensation. In fractionation, temperature and pressure are varied to separate the fluid fractions. Now stop the tape and go to Workbook Period 2.
You've just completed the first 2 periods of the program. You saw the structure of matter and how pressure affects that structure. The next section will deal with the differences between heat and temperature, how we measure heat, and why we use certain fluids in heating and cooling systems. You probably remember our model of matter from the first part of the program. Well, let's look at it again.
All matter is in motion. The amount of energy it has will determine its phase. Now let's consider heat and temperature. They're not the same. Heat is the total kinetic energy of all the molecules in the substance. Kinetic energy refers to the energy of motion. This energy depends upon mass and the total speed of the molecules. Temperature, on the other hand, is a measurement of the average kinetic energy of the substance. In any substance, some molecules move faster than others. Temperature gives an average value for molecular motion. This is an indirect way of measuring the heat in a substance. For example, which of these samples of water has more heat, the gallon or the cup? There are more molecules of water in the jug than there are in the cup. Heat depends upon both the total mass and total motion. Since the temperatures are the same, we know that the average speeds are the same. The gallon contains more heat because there's more water in it.
When we measure heat, we use BTU, which stands for British Thermal Unit.
1 BTU represents the amount of heat necessary to raise the temperature of 1 pound of water 1 degree Fahrenheit.
Many materials require less heat to change temperature. The property that represents this heat requirement is called specific heat. The unit for specific heat is BTU per pound degree Fahrenheit.
The specific heat of water is 1 BTU per pound for every degree. Think about this question. If a 1 pound piece of metal heats up faster than 1 pound of water, will its specific heat be less or greater than 1? Most metals are good conductors of heat. They require less heat to change in temperature than water does, so their specific heat is less than 1. This graph will show something interesting about water. The specific heat of water varies with its phase. Water as a solid requires 0.5 BTU for 1 pound to increase by 1 degree. In the liquid state, the specific heat is 1.0 BTU per pound per degree.
And in the gaseous phase, the specific heat returns to 0.5.
What does that mean for you on the job? If you'll be working with water in a liquid form most often, you should note that liquid water needs more heat to increase in temperature than water vapor or ice. This is especially important in a distillation tower, as we'll see later. The specific heat values and the heat content of water vary with temperature. Heat content is important because the heat can be used for various processes at the plant. There are 2 types of heat. One is sensible heat. It can be sensed or registered on a thermometer. The second type is called latent heat. Latent heat affects phase and is hidden from the thermometer. The following graph will show what this means.
The solid phase of water absorbs 1 BTU as its temperature increases 2 degrees. If the temperature increases from 0 degrees Fahrenheit to 32 degrees Fahrenheit, it has absorbed sensible heat, since the thermometer records an increase. At 32 degrees Fahrenheit, however, the solid begins to melt. Now the heat being absorbed is used to increase the energy of the molecules and move them apart. This heat is latent heat because the temperature stays the same until all the ice is melted. Here's what happens as liquid water goes from 32 degrees Fahrenheit to 212 degrees Fahrenheit. All the heat being absorbed increases the water's temperature. This again is sensible heat. The next step requires a lot of heat to change the liquid into a gas. Water's latent heat of vaporization is 970 BTU per pound, a significant difference from the 144 BTU needed to melt ice. The temperature can go above 212 degrees if the pressure is high enough. This vapor is superheated steam.
Just as latent heat can be absorbed as phases change, this heat can be released. As this happens, we can use it for heating purposes. There are many uses for latent heat in a refinery. For example, at the base of a fractionating tower, the steam condenses and loses heat to the processed liquid. The amount of heat given off is the same that was absorbed, 970 BTU per pound. This heat is used to separate fractions from the processed fluids. A substance with a high heat of vaporization provides a lot of heat as it condenses. This type of substance is best to use for heat exchange.
Cooling can also take place by using a fluid's ability to absorb or gain heat. The best example that shows this is Freon, a liquid with a low boiling point. It absorbs heat as it evaporates. It is then passed into a compressor which condenses it, and the cycle begins again. In period 3, you learn that heat and temperature are different. At equal temperatures, the greater mass has the most heat. BTU is the unit used to measure heat. As water changes phase, its temperature does not change. Fluids can be used to heat and cool. Now stop the tape and go to Workbook Period 3.
The next 3 sections of the program will be dealing with measuring properties of fluids. These properties include pressure, temperature, density, specific gravity, and viscosity. In any part of the petroleum industry, pressure and temperature represent variables that must be controlled. In order to be controlled, they must be measured. You as a worker must be familiar with these measurements and what they mean to do your job effectively and safely. The measurement of these 2 properties, pressure and temperature, will be discussed in this section. We'll look at pressure and how it's measured first.
As you learned earlier, pressure is a force per unit area. The force is usually represented in pounds, and the area is given in square inches. The unit is abbreviated PSI.
In addition to PSI, you'll see that other units are used that relate to specific conditions of pressure. Other units that measure pressure are PSI-G, pounds per square inch gauge, PSI-A, pounds per square inch absolute, PSI-V, pounds per square inch vacuum. We'll discuss their use as we continue through this section.
Pressure in a vessel, inside piping, or at a pump is usually measured with a mechanical gauge. Most gauges show pressure by a hand that moves across a dial. Getting the hand to move accurately with the change of pressure is the job of the Bourdon tube. The Bourdon tube by itself consists of a piece of hollow, flexible metal. Because the metal is hollow, the fluid enters it. The metal bends with changes in pressure. As this happens, a mechanical linkage moves the hand. A pressure gauge measures the pressure of the fluid in a pipeline or vessel. Gauge pressure is represented as PSI-G. PSI-G does not include the pressure exerted by the atmosphere. Another way of measuring fluid pressure is by using a mercury manometer. The manometer is a U-shaped tube. The vertical sections are often referred to as legs. The tube is partially filled with mercury, a liquid used in thermometers. In this example, both legs are under equal pressure, that of the atmosphere. The levels of mercury are the same. This manometer is connected to a pressurized gas line. Note the difference in levels. The pressure of the gas forces the mercury down in the left leg and at the same time up in the right leg. We can get a measurement of the gas pressure by finding the difference between the levels of mercury. This can be measured in units that measure distance, inches or millimeters. This distance represents the height of the column of mercury that the pressure can support. Another instrument used to measure pressure is the mercury barometer. This directly measures the atmospheric pressure. Its units are inches of mercury. As you know from weather forecasts, atmospheric pressure varies with the weather conditions. Normal atmospheric pressure at sea level is 29.9 inches of mercury. That's equal to 14.7 psi. This is a measure of absolute pressure, that is, total pressure on the surface of the Earth at sea level. Often it's important to use and consider absolute pressures on the job. To get these absolute numbers, you'll calculate them from a gauge pressure. PSIA, pounds per square inch absolute, represents the gauge pressure plus 14.7. This gives the total pressure on the fluid. So far, we've looked at instruments to measure pressure: the Bourdon tube in the mechanical gauge, the mercury manometer, and the mercury barometer. And the units to measure pressure: PSI, PSIG, PSIA, inches of mercury, and millimeters of mercury. Now let's take a look at the temperature measurements. The most common way of measuring temperature in the U.S. is with the Fahrenheit temperature scale. This scale represents the freezing point of water as 32 degrees and the boiling point of water as 212 degrees. Another scale you may be familiar with is the centigrade or Celsius scale. The freezing point of water on this scale is 0 degrees, and the boiling point is 100 degrees. As you remember, matter is made up of molecules in motion. As temperature decreases, motion and energy decreases. If we could decrease the temperature to a point where all motion stops, we would reach a temperature known as absolute zero. Temperature scales have been developed to include absolute zero as the starting point, or 0 degrees. Here are two absolute scales. The first is called Rankine. When we compare it to the Fahrenheit scale, we find that there is a difference of 460 degrees between the two. Absolute zero is minus 460 degrees Fahrenheit and 0 degrees Rankine. The freezing point of water is 492 degrees Rankine and 32 degrees Fahrenheit. The other absolute scale is called Kelvin. Compared to the Celsius scale, it varies by 273 degrees. Absolute zero is minus 273 degrees Celsius, or 0 degrees Kelvin.
The reason that temperature is so important is that as temperature increases, the molecules of matter move apart, taking up more space.
Look at this example. The liquid at room temperature is at an even level in the flask and in the glass tube. But as heat is added and the temperature increases, the fluid level rises in the glass tube. This demonstrates the expansion of a liquid. When we store liquids in tanks, the same thing happens. The level of a liquid can be misleading because of expansion. Because of this, standard temperature has been established for measuring the volume of fluids. This temperature is 60 degrees Fahrenheit. In this section, we reviewed the instruments to measure pressure, the units to measure pressure, and finally, the temperature scales, including Fahrenheit, Rankine, Celsius, and Kelvin.
In the workbook, you'll be introduced to another method of measuring pressure on the job referred to as PSI vacuum. Stop the tape and open your workbook to period number 4. In the last section, you learned about the measurement of temperature and pressure. You saw that the volume of liquids changes as the temperature changes. Another property of matter related to volume is density.
Density is the weight of a substance divided by its volume. Let's use water, for example. 1 gallon of water weighs 8.33 pounds. So its density is 8.33 pounds per gallon. Liquid density is usually measured in pounds per gallon. Gas is usually measured in pounds per cubic foot.
In the previous section of the program, we saw that as temperature increases, the volume increases as well. Density is inversely related to temperature. That is, as temperature increases, the density of a substance decreases. Let's look at a model to better understand this relationship.
Given any substance, when a specific volume is heated, expansion takes place. After heating, fewer molecules occupy the same space. The same volume weighs less, so the density has decreased.
When heated, gases undergo a greater change in volume than either solids or liquids. In addition, gas volume is affected by changes in pressure. For these reasons, standards of both temperature and pressure must be used when measuring gases. In measuring gases, the temperature standard is 60 degrees Fahrenheit, and the standard pressure is atmospheric pressure, or 14.7 psia. When referring to a liquid, how would you describe its heaviness? Density is one way to describe liquids, since it identifies the weight of a specific volume.
Another way to describe weight is to compare the liquid's density with the density of water. This results in a number called specific gravity. In order to get the specific gravity for liquids, we compare their densities to the density of water. And to get the specific gravity for gases, we compare their densities to the density of air. The specific gravity of gases is very important in the hydrocarbon industry. An accumulation of a gas that has a high specific gravity can be a life-threatening danger for workers.
When working with petroleum liquids, the unit used to indicate heaviness is the degree API. To understand what this unit means, let's look at the instrument that's used to measure it, the hydrometer.
You may have used a hydrometer to check your car's battery fluid. It's usually made of glass with lead shot at the bottom. The hydrometer is placed in the liquid being measured. The liquid will have a buoyant or upward force on the hydrometer. Just as a boat floats higher in salt water than in fresh, a hydrometer will float higher in a denser liquid. This means that the reading will be a lower number on the scale.
With this in mind, what's the relationship between API gravity reading and the density of a liquid? The lower the API gravity reading, the higher the density.
To measure the heaviness of non-hydrocarbon liquids, the Baumé scale is used. It is measured in units of degrees Baumé.
Using tables and graphs, you can convert one measure of a liquid's heaviness into another. The workbook will cover these conversions.
To summarize, there are 4 ways to measure a liquid's heaviness: density, specific gravity, API gravity, Baumé gravity. Now stop the tape and go to workbook period 5.
You've covered basic information on the structure of matter, pressure's influence on fluids, the difference between heat and temperature, how to measure temperature and pressure, and the importance of density. The last section will deal with the viscosity of fluids. The definition of viscosity is a fluid's resistance to flow. All fluids have viscosity. Let's look at two liquids and compare them. I'll place a drop of each liquid on this glass, and when I tilt the glass, you'll see which has the greater viscosity. As you can see, the slower liquid is the motor oil. This means that it has a greater resistance or opposition to movement. It has a greater viscosity. Though this demonstration was simple, it's basically the same way in which viscosity is measured in the lab, by timing the flow of a liquid. Viscosity is caused by friction or drag resulting from the intermolecular forces of liquids. If the amount of friction is high, then more time will be needed for the liquid to move. The intermolecular force decreases when heat is added to a liquid. When this happens, viscosity decreases. The viscosity of a gas, on the other hand, is influenced by the friction produced by molecular collisions. The number of collisions increases at higher temperatures. So if the temperature increases, the viscosity of a gas increases. How does density influence viscosity? A gas that has a high density will have more molecules per unit of volume. This increases the likelihood that collisions will take place. So, with all other factors equal, the denser the gas, the more viscous it is. Here, the most viscous gas is butane. Since temperature is a factor that changes viscosity, the temperature must be standardized for its measurement. Let's look at how this is done. This is a Sable laboratory viscometer. The tube containing the liquid to be measured is kept at a constant temperature by a water bath. Then the flow of the liquid is timed in seconds. The number of seconds gives us an idea of how viscous the liquid is, but this isn't an absolute measurement. In order to measure absolute viscosity, three factors must be considered: amount of flow, or the weight of the liquid, distance, how far it travels, and speed of flow, or how fast the liquid is. All three of these must be considered if different fluids are traveling through the same pipe under the same pressure. To do this, a new unit is needed. The unit that measures absolute or dynamic viscosity is the centipoise. As with other measurements, water represents the standard for viscosity. At 68.6 degrees Fahrenheit, the absolute viscosity of water is 1 centipoise. You may come across an online viscometer that measures in absolute viscosity units. If you see a reading of 2.0 on this type of viscometer, you'll know that the liquid being measured is 2 times more viscous than water. However, more viscous doesn't always mean denser. In liquids, the chemical properties have a significant effect on the molecules. For example, water has a greater density than motor oil, but the oil is more viscous. To show the relationship between absolute viscosity and density, a measure called kinematic viscosity is used. It compares the liquid's absolute viscosity with its density. Kinematic viscosity is measured in a lab with a special instrument that measures flow in units of time. The measurement is taken in the lab and then converted to a unit called centistoke. One reason for finding kinematic viscosity is to determine how much the liquid changes with temperature. This is especially important with motor oils. There are two ways to determine how temperature affects the viscosity of an oil. First, the viscosity index indicates how stable the viscosity is with temperature changes. The higher the index number, the less the viscosity changes. The second method is the temperature viscosity graph. The workbook will go into more detail on how to make use of this graph. To summarize this section, we first showed that viscosity is the resistance to flow. Second, that the relationship between density and viscosity is different for gases and liquids. And third, that to measure viscosity, specialized instruments and unique units are used. This concludes the video portion of our program. We've covered a lot of information about the characteristics of fluids. To check your knowledge, make sure you work the exercises in the final section of the workbook.